found level 45.
All right, so let's begin with so we'll begin with the fourth sort of topic. So we did the structural properties, the pattern mining, the clustering, and now we're going to talk about classification. So what is the classification class? So classification, right, is that you have, in this case, it's also a supervised learning problem where you know the labels. Okay? So in that sense, it's a little bit easier than clustering. So clustering, we don't have any labels, we just have a graph, we want to sort of partition it. Here, we're going to have a graph, and we have labels. So you may have labels on the nodes, as one example, and you may want to predict the label of some other node. Right? So I give you a new node for which you do not know the label. Then the idea that can you predict the label for that. So as you can see, this has many applications. This can be used for recommendation. You know, this could be used as a way of partitioning your network in terms of basically, but it's more of a predictive kind of a task. That way you do not know the labels and you want to do it. And then there is the other scenario where you have many graphs and you have labels for those and you want to predict. So let me try to sort of first define the problem that we want to solve, and then we'll see what are the methods we can use. So just like in pattern mining, there are these two situations where you have either a database of many graphs or you have a single large graph. So we'll have the same kind of a situation here. So we'll start with the easier one first, easier sort of conceptually to sort of think about in terms of, because it's sort of it's very close to the normal classification. So here the point is that you have what we call a graph database. Okay, that means you have graph 1, you have graph 2, graph 3, many graphs. And you can have literally millions of graphs. Okay?
You change the color.
Oh, okay. So you have lots and lots of graphs in your database. But now the idea is that you also have a label for each graph. Okay, so the entire graph gets a label. So that means this is the graph. You'll say. So now we define this is from class 1. This is from class 1. This is from class 2. So actually, I'm going to be using basically just two classes, okay? But you can generalize this to more classes. I'm just going to call it positive or negative class. So like a binary, But generally it can be k number of classes, but it's probably just easier to think about positive and negative. So I'm just going to call that positive class, positive class, and so on and so forth. These are the labels or the classes. Okay, so this data is given to you. Okay, there is a labeling, someone has done that labeling, some expert has done it, or some other means. So every graph has a label, positive, negative. Now, a new graph comes in. Okay, so some graph you've not seen before, gn plus 1. And the question is, you have to predict what is the label. Right? So you're given a bunch of data. This data is your training data, right? So this is the classic sort of difference between clustering and classification. In classification, you are given a training set. You're allowed to look at the real answers, the correct answers, but you have to do everything else. You have to figure out what is the mapping. So that mapping is your classifier, right? So basically what we're doing is given this information, we have to build a model or a classification model or a classifier that can essentially do this prediction for us. So this is the input set or the training set. And this is an example of a test case or test instance. So the idea is that you have past information with labels. You build a model. So I'm going to call this model, a function f, which is our classifier or a classification model if you want. And this function that you learn, it has to extract, in the case of graph, it has to extract whatever it needs from the input data, right? From the graph G1, G2. So it has to learn what is the mapping, what makes this a positive case, what makes that a negative case. So we'll talk about exactly those techniques, how to extract those features and then how to build the classifiers on top of that. And then once you have that, simply take that function and I can just apply that. I can say f of gn plus 1 is my predicted label. So that's essentially how you apply the model. So once you build the model, you plug in any other graph, it's going to spit out the class. So where does this kind of problem appear? So let me give you a very good example. So think of chemical compounds. Okay, so this is widely used in drug design and in pharmaceutical industry. Each graph is a chemical compound. So it's pretty much a component of a drug or something like that. And this positive and negative basically means that this drug or this compound might be effective for that disease. Okay? So think of some, even a common cold or fever, whatever. You say, if I have many, supposing I wanted to come up with a new medicine for fever, I'd say this chemical compound is known to inhibit, or bring down the fever. So that would be the positive case. This one is known not to do that, so it's a negative instance. This one is known to do that, not, So maybe fever is a trivial example because we have many good drugs for that. But for some cutting edge, the pharmaceutical industry is always spending a lot of money doing, research and development of new drugs. So they are constantly faced with this problem, that they know certain properties of those drugs, and you can now synthesize a new drug, right? A new compound, and you want to know whether or not it will help. And so the more it is similar to those things that help, cure the disease or at least, tackle it somewhat, the better off you are. So that's one example. Let me give you another example. This time from, let's say, bioinformatics. Okay. So now we have the, the ability to measure the gene or the protein content of a cell. And so what you can do is, let's say, for example, in the case of cancer, right? So it's and let's say for some extreme cases, you can actually measure at the molecular level. What is the? So you want to know what happens in a normal tissue, so like a normal cell, a healthy cell, versus a cancerous tissue, right? So a cancer cell. What are the different proteins being expressed? What are the different genes present in that cell? So you can take a cell, you can measure the protein content, and if you can then somehow, look at the observations either in space or in time, and you can create a graph out of that. You can say in healthy tissue, right? So the label would be healthy tissue. This is the set, this is sort of the gene interaction I'm observing. In cancerous tissue, this is the sort of, a graph I'm observing. So if you can collect different instances at different points in time, for different people, right? So the different graphs can be coming from different people, for example. Again, the point is that once you do that, it says, okay, now you have a data set which you have modeled as a graph in some way, and that has a label. So this is healthy, this is diseased. Healthy, disease, healthy, disease. Now you want to know, okay, in terms of the genes that are present and the interaction between them, what is the, can I come up with a model to predict? So if I give you now, so a new patient comes to the hospital, you can look at their, tissue samples, and then you can basically see whether or not, they belong to the healthy or that category. And then you can do similar things. So anytime you can take a data and model it as a graph, or multiple instances of graphs with labels, then you can apply this kind of a, situation where you can learn a classification model to predict the class. So this is one scenario. The other scenario is more like a social network type of scenario, where you just have one large graph. Okay, so let's talk about that. So that's also a obviously interesting case. So here you have a single large network. Okay, so there's only one graph G, and there are nodes. Okay, now in this network, the labels are attached to the nodes, for example. Okay, so nodes will have classes. You say if it's maybe think of it this way. So if this is a social network, so you need to now say that this person belongs to a certain class. Now it depends on the application, but the classes could be different interests that they might have. They said these guys are all they have the same interest, if you will. This guy has a different interest, and these two have similar interest to that one. So you can give a label to each node, but that's your training data again. So that means I've given you the graph, I've given you the node, I've given you the actual classes that they belong to. But now think of it this way. A new node is there which you have not seen before. Okay, so here's a new node that comes in. It connects to that, it connects to that. Now, okay, so these are all labels. Okay, so I'm going to say the class is positive class, positive class, positive class, negative class, positive, negative, and negative, positive, negative. So now the question is, what is the class of this node, right? So again, the same general idea is the same, that you know the labels of existing nodes in the network. Okay, from that you have to learn something. And when a new node comes in, you need to be able to predict the label for that node. That would be an example of a classification problem. So here you have to predict the label, and again you have to learn the function from that. And the classes, as I said, can be more than just two. I'm just using positive, negative because it's easy to sort of describe that. But generally, in real world, so for chemical compounds and those things, generally the two classes are a good approximation, because they generally have the class of interest and everything else. In a social network, probably you'll have more than two classes. You'll probably have many different groups or things that you want to describe. As a very quick example, think of this as a Twitter graph. Okay, so these are retweets and things. And let's say we put the node would be let's say the political affiliation. Okay, so they belong to the Congress, or they belong to the BJP, or whatever, right? Or whatever other party you can think of. Or in the US, it would be Democrats versus Republicans versus third independent candidates. So those could become the labels. And so your point would be, before elections or during some other events, you have the whole social network. People are talking about certain things, and you know who belongs to which party, and you try to learn a model from that. And then maybe a new person, like maybe an independent voter you haven't seen before, right? They tweet something, you want to know, are they supporting that party? Are they opposing it? What's the situation? So this can be applied in many scenarios where you really want to make some sort of a prediction for unknown things. A more maybe interesting, from a biological perspective would be, you have genes and proteins, and you know the biochemical, the biological process or the function that they're involved in, and a new gene for which you do not know the function, can you infer what is the function of that gene or protein based on the labeled data? So this is again a question of, you have partial information, you need to know the rest. So classification is basically that coming up with a classifier that can do this mapping. Now the question is, how are we going to basically go about doing this in a graph situation? So let me first tackle this situation, the graph database scenario. Okay, so you have a lot of graphs, because the kind of techniques that we're going to be using are going to be, they're sort of similar in the end, but let's just look at them separately and then we'll see what the common threads are. So the first thing you have to do is, if you think about this problem, because again, as I said, conceptually a little bit easier perhaps to see, you have to define similarity and differences. Again, it's sort of, the same thing that we did for clustering, you have to do implicitly at least for the classification also. Because there are certain properties of G1, G3 that make them from the positive class. And likewise, there are going to be certain properties of G2, Gn that will make them the negative class. So the idea is to elucidate those properties. Can we extract those properties? So that essentially is the task of feature extraction. Okay? So classification is pretty much sort of enhanced feature extraction. If you have good features, you'll be able to do better classification. So they go pretty much hand in hand. So, and by feature extraction, the whole point of feature extraction is to compute similarities. Okay, so this is where we tie in the notion of, again, similarity or a distance. So the more features you have in common, the more similar you are, right? So that's the basic idea that we want to basically exploit. So situation is that you're given a graph database D, graph 1, graph 2, graph n. Of course, they are all labeled. So actually, there is a, like I said, the corresponding label with labels. Okay, so based on what we have learned so far, we can easily think of certain ways of extracting features. So what you can do is, so assuming that there are positive and negative, so let's assume that for now there are only two classes. So you take your data set and you divide them into two parts. Make it D positive and D negative. If you had more, you can do more parts. So that's not the real problem here. So what is this? This is basically all those graphs that have, that belong to the positive class. So let's just say this was positive, this was negative, and so on and so forth. So this would have G1, this would have G2, whatever. I mean, so there's a whole bunch of graphs: G10, G20. This has G3, G4, and so on. So you have basically split your data into two parts. And the reason I did this is because I wanted to study what makes these graphs similar, what makes these graphs similar, and of course I also probably want to compute the cross similarity between them. So the idea is that I want to define now or compute some sort of a distance function or a similarity function between any two graphs. So I would like to come up with this, the distance between Gi and Gj. Okay? This is what you really want. Now you can do it by splitting, because I'll show you the sort of the thought process that I had in mind. But we can do more things. But this is what you really want to know, is how to compute this. Actually, let me change that to similarity, because I'm going to be talking about, so I mean distance and similarity are pretty much inverses of each other. But we think in terms of similarity, how similar are they? And the more similar they are, hopefully things in the same group or the same class are similar, and they're dissimilar from that. That will be easy to discriminate. But it's not always so easy. So then later on I want to tie this notion to the notion of the kernel. Okay? So that's where I'm basically heading. Because the kernel is this, the kernel matrix is the one that will help us define similarities. So I'll get there. When I get there, I'll mention that. So now you have the situation and you want to define this. So based on what we have learned, okay, tell me or think of how I might be able to compute similarity between any two graphs. Any ideas? So I give you these two graphs, right? So there's G1 and G2. I mean, the Gi and Gj. And I want to know how similar these two graphs are. How might we do this? Good. So we can definitely use structural properties, right? So that's one idea. That actually use the structural properties.
Can we compare the spectrum of this two?
Absolutely. The spectrum is going to help us also. Yes. So that's part of the structural. So when I say structural, so that's exactly, in fact, one of the key ideas there is that we can compute not just, we can compute several things, not just eigenvalues, eigenvectors. We can use pretty much, so you want to compute the similarity between Gi and Gj. Okay, so one idea is structural. Structural properties, or let's call them structural features. Okay? So the idea again is I'm extracting features from these graphs. Right? So if there are two graphs, I need to be able to extract features. So what are the features I can extract? Well, definitely the spectrum. So what I can do is I can look at the eigen spectrum. That is basically for GI, what are the lambda values, lambda 1, lambda 2, lambda n. Same thing for GJ, right? Lambda 1 prime, let's say lambda 2 prime, lambda n prime. So you can get a whole bunch of numbers out of the eigenvalues. You can compare them. You can probably just sum them up and see how similar they are, for example, right? So in other words, you have to now compute some function of those, of course, to see how similar they are. You have to define some function on those set of numbers.
Sir, but the number of latent roots in these two graphs not same.
They're not, yeah, exactly. So they may not be the same. Normally what you're better off doing is you're better off looking at the top one or two, right? The largest eigenvalues, the dominant ones. So you don't have to look at the whole thing. But so definitely the largest one. So you should definitely look lambda 1 versus lambda 1 prime, right? So the distance between them. There's a large gap, that means there's some, they're not going to be more or less, there's a problem in terms of the matching. You can also do the sum, right? So this will take care of your, different numbers, for example, issue. So people have done all these things actually. They have looked at the largest, the sum. You can do path length. So like what is the average path length, right? So path length. You can do the diameter. I mean, pretty much you can measure a whole bunch of things. Pretty much any property that we have learned from the first lecture. Right? I can compute either for the whole graph. I can compute the clustering coefficient, right? I can compute the average degree, the average path length, the diameter. All those things I can. Now each one of them become the feature. It's not, so now I have a whole bunch of features. So think of this as you compute all kinds of structural features, and then you simply describe in the end. You say GI. Okay, so here's how you describe your data in the end. You say every graph, so this whole data set of graph, you basically extract a bunch of features, F1, F2, FQ. This one can be, the largest eigenvalue, right? So the lambda 1 value for each graph. This could be mu L, the average path length. This could be the average degree, right? So each one of them become the value, right? If I compute for the whole graph GI, so then this I can put GI has eigenvalue 5.1, okay? Average path length is 6. Average degree is 10.2, right? Likewise. So basically, what is the average between us? What is the average clustering coefficient? Each one of them become the feature, pretty much. What you've done is you've basically mapped the graph into a totally different feature space. It's a feature space which is composed of structural features. And now this becomes a regular point in a very high dimensional, depending on, so it's a Q dimensional space. And maybe things are correlated, because certain properties are known to be correlated with each other, but that's fine. We'll just compute as many features as we can think of. Literally hundreds, thousands of features we can compute for a graph. These all have to be global features, meaning from all the nodes, we either have to average them, take the max, take the min. You can do whatever, but it has to be a feature for the entire graph. Okay? That's why I'm talking about average path length, average degrees, some of the eigenvalues, the largest eigenvalue. And you represent Gj by the same, way. So this could be maybe 4.8, 2, 2.1, and so on, right? So now, these two graphs are basically described by a bunch of values. And now it's easy to compute similarity between them. I mean, I can basically pretty much do, a dot product between those two, which is the standard way of defining similarity. So you just take the dot product. This times this plus that times that plus that times that. And so the higher the dot product, the more similar they are. So dot product, and I'm mentioning dot product in particular because that's the fundamental similarity notion for vectors. For two vectors, and it's a linear notion, right? So dot product is a linear operation. Given the input vector, we don't manipulate anything else. We simply take the dot product. So I can just say that, basically what I'm doing is I'm taking gi and mapping it into some vector xi. I'm taking gj, mapping it to some vector xj, and then I'm just doing a dot product. I'm saying xi transpose xj. This will be my kernel between g1 and g2. Sorry, gi and gj. So in other words, I had to go through the cycle of feature, extraction essentially, because just given two graphs, what can I do with it, right? I have to obviously do something to be able to compute the similarity. So that's one thing. Now the interesting thing about this idea is that, this will again when I mention classifiers later, and I'm literally, I'm calling this a kernel, because this notion of similarity is actually a very well-defined notion of a dot product between two vectors. So that means it is an algebraic operation that we're doing in some vector space, and later on I'm going to talk about some properties of the kernel, right, that we need to have. It will, we can show that if you look at all the pairwise similarities, this will lead to what is known as a positive semi-definite kernel. Okay, so again, you get that positive semi-definiteness idea. So that means it has very nice properties. Okay, it has a well-defined sort of meaning. So these are sort of all ideas sort of are in a way interrelated to each other. Random walks, kernels. This time the kernel is over a different type of it's between two graphs as opposed to just a single graph. So those are the things that we'll be basically trying to cover. So this idea is simple. This is good. What other features can we do? So I've just done the structural part. Give me another way of extracting features based on what we have seen already in the lectures. What else can you do to compute similarity between two graphs? Pattern mining, exactly. So second thing is we do pattern mining. So conceptually, essentially what we're saying is, right, we're leaping from sort of structural, sort of local, or whatever, paths and things to subgraphs and those kind of things. So two graphs are going to be similar, the more subgraphs they have in common. Right, so if I can enumerate the subgraphs, then I can say, okay, does this pattern have this subgraph, does this one have this subgraph, and I can even compute, how many things they have in common. That will become the score. Right, so the idea here is, so this is a second sort of, set of features. So this is basically extract subgraph features. Okay, now let's talk about the subgraph features. So I'm going to now describe again there are two sort of main ideas here. One is the frequent subgraph. And the other is the notion of a graphlet. They're very related to each other, but they're slightly different. Frequent subgraphs we've already seen, right? So essentially all you have to do is, and this is where the division actually helps. So if you want to do frequent subgraph mining, the basic idea is you start with your database, you divide that into the positive half and the negative half, okay? From each one of them, now I have multiple instances, right? So I can do the frequency computation within each group. So I'll say which patterns are frequent in the positive set. So find out basically all frequent patterns in the positive class. And basically do the same thing here. So I'm just going to call that f of p. Okay? So this is going to be defined as f p. And from here you basically extract f of n. So this is all the subgraphs that are frequent in fp, independently of being frequent in fn. So I'm going to do basically two different processes. Okay, mine this separately, and extract the set of all the frequent patterns, the set of all the frequent patterns. Now, remember our goal is to classify, to basically discriminate. If a pattern is frequent here and it's frequent here, is it of any use to us? No. So we want to basically throw those patterns out. So anything that's common to both classes is not able to distinguish between those two. Whereas our whole goal is to distinguish between the positive and the negative. So what you do now is you do sort of a cross, elimination. Basically, you say anything in common, throw it away. So the idea is that now remove patterns or subgraphs common to both. Now, whatever survives, hopefully, those will now become the features. Okay? So I can say that I can turn each subgraph will become a feature. So actually, if you think of it this way, it will be, again, I'm converting this into a binary example. You take your after doing this, let's just call the filtered set f is basically filtered fp plus filtered, actually let me do it the other way around. Right? So basically take the union of all the patterns and remove the thing that are in common. So we do this. Now this is basically now a set of features. Features means they're subgraphs. So let's just call it subgraph 1, subgraph 2, subgraph P. Now any given graph, G1, you just say, is the subgraph present in that graph or not, right? So I can just turn it into a binary feature vector. So every subgraph in this set, so this is your set F, okay? All the subgraphs in that set, they're now either going to be appearing frequently in the positive or they're going to be appearing frequently in the negative. So now pick G1, and if G1 is from P, right, it's from the positive class, let me use something else here, G or R or something. So if it's from the positive class, let's say this one was actually, from the positive set, G3 was from the negative set, G4 was from the positive set, G5 was from the negative set. So this one is more likely to contain this, maybe doesn't contain that, doesn't contain that, contains this, doesn't contain that, and so on, right? So what I've done is I've taken a graph and I've basically turned that into a binary vector. Whether the subgraph is part of the input graph or not. The frequent subgraph is part of the input or not. And likewise you can do for G2. Now if G2 is from the negative class, it should not have any from the positive. It may have G3, it may have G4, it may not, it may have G5, and so on. So the idea is that whatever subgraph it contains, we put a 1, otherwise 0. And now again I can define a similarity between them. This time it will be a binary similarity if you want. It can again be done in terms of dot products. But it doesn't even have to be, just the, you can actually compute more sophisticated things. This is just, I'm saying, just showing you one of the most simplest ways of, computing a feature vector. Because it may happen that G1 actually contains that same subgraph many, many times, right? So you can actually put down not just whether it contains it, if you look at all the embeddings, you can say how many times does that subgraph appear in G1. So it doesn't have to be binary. It can be, this subgraph appears twice. Okay, this appears only once. This subgraph appears 10 times. Okay, so you can actually put the number of times that subgraph, like in this case, in the small subgraph G1, appears in the big input graph from the database. So the idea is that for every graph in the database, I have to compute a feature vector, and then I can define the similarity between them. Now, one thing that is worth mentioning here is that let's see, what I wanted to say was, so you do the frequency, and then you get the features. Oh yeah, the thing I want to mention is, this condition here is actually a very simple condition. So I just said, if things are frequent in both, then remove, right? But the point is, you can do something more sophisticated here. So, you can do actually some sort of a discrimination score. So you can say, to what extent is the pattern, so it may happen in both, it may be frequent in both, but maybe here the frequency is much higher, right? So that means there is a big difference in the, so in terms of frequency, yes, they're both frequent because I have to choose some threshold of frequency. So we can say that actually we can just compute some sort of a discrimination index. I can say the support in dp minus the support in dn. Okay, so I can actually compute how much of a deviation there is between them. So you can do many more interesting things here. Not only that, you can do statistical significance, as I'm going to show shortly, using the graphlet idea. So let's go back now. So this is basically based on the frequent subgraphs. Okay, so I'm not here talking about the graphlets. So this is basically idea number 8, where you can do frequent subgraph mining, then you do some sort of a discrimination to extract, patterns that are not similar. But here's the graphlet idea. So the graphlet idea is that I can actually compute the complete distribution. So basically, still you want to extract frequent patterns, but now the second idea is that of graphlets. Now the key difference is frequent subgraph mining can discover larger patterns, but it only discovers frequent patterns. Right? So you have to define what frequency you want. A graphlet, on the other hand, will be the complete probability distribution up to a certain size. So you have to obviously restrict the space. So let me just show you what the main idea looks like. So if I look at a graph like this, the notion of graphlets is basically find the distribution frequency distribution for all subgraphs up to size k. So the idea here is that we don't do any pruning. Okay? I want to know the exact frequency distribution of all the subgraphs up to a certain size in each graph. So given this graph, let's call this graph GI. So the number of edges is not that interesting. So let's start with size 3. But if you want, we can so the first feature would simply be how many patterns of this size do you have? Well, there are 1, 2, 3, 4. So there are 4. The number of times a single edge happens is 4 times. Now remember, we can always do labeled stuff if you want, right? Right now I'm just showing everything from an unlabeled perspective, but you can always add labels. So the first thing would be how many labeled patterns up to that size you can have. But generally this work was done from a purely structural point of view, so they ignore the labels. They just say how many structural subgraphs you have. So I'm going to do it from the structural subgraph point of view. Then the next thing would be triangles, right? So how many, and by the way, when I say all subgraphs, I mean all connected subgraphs. And so now I can go and count how many times do I see, so, well, now it's a little more. So this would be 1. So it's easy to actually, I'm going to number them for our own,
5.
It's 5. Okay, so 1, 2, 3. So that's 1, 2, 3. 1, 3, 4. 1, 3, 4. 1, 2, 4, right? Then you have
1, 4, 3.
1, 4, 3.
no 1, 4, 3 is the same as 1, 3, 4. Oh no, okay, okay. In terms of the 1, 4, 3. All right, you get the idea. So it's plenty. So you have to count all of these. So 2, 1. Okay, yeah. So now you basically put everything in the middle here. So you have to do that. So whatever, right? So you just count how many times it happened and you put the frequency there. Okay, so it's obviously greater than equal to 5, whatever that number is. And then the third would be, in this case, the triangle. And the triangle is only 1 axis, right? One. Yeah, 1, 3, 4. Okay, now one thing to keep in mind actually, and this might change the counts, that once I do 1, 3, 4, okay, if you permute, like 3, 4, 1, 3, 3, 4, 1 or 4, 1, 3, it is the same pattern, okay, so you do not overcount. Same pattern which has what we call automorphic, if it's automorphic to itself, we still count it as only one, because it has to be distinct mapping, not the same, or just a permutation of the same number. So in fact, actually, right, so we have to go back here and actually, the point would be, because these are unlabeled, right, so the numbers do not matter, they have no meaning actually. So this one would not be considered. This is not valid. Because once you did 1, 4, and 3, right, they're all the same labels actually. So think of it in terms of labeled structures. They're all isomorphic to each, so 1, 4, 3, 1, 3, 4 doesn't matter. Maybe. 1, 4, 3. 3, 4. 1, 3, 4. Actually, you're right. Okay, no. So in this case, it is fine. So only the isomorphic one, yeah. So we don't have to have the other way around. We don't have to have 3, 4, 1 and all that sort of thing. Yeah. So this is still fine. So the problem is you could do size 4, right? So and then finally, if I want to do size 4, there may be many subgraphs of size 4, but I'm not going to list them all up. So you choose some value. So in this case, let's say k equal to 3. So then I'm going to stop here. Okay. So these are all the subgraphs of a certain size. But the interesting thing is, you make a frequency plot. Okay, so this would be the frequency, or if you want, you can turn it into a probability. It doesn't really matter. G1, G2. So for every graph, okay, you put the frequency. So this would be, so this is G1, this is G2, this is G3. So, G2 is somewhere over here, maybe, I don't know, 8 or something like that. Greater than or equal to 5. And then this is only 1. So you basically get a frequency distribution. So this is going to be this, it's going to be this. So this distribution, right, is what we look at. So now I can compare two graphs based on their graph-led distribution, essentially. So the idea is enumerate all possible subgraphs, count them all. Many of them will be 0. The things that actually appear, you put them, and now I can compare two different distributions. This is the distribution for G1 or GI. You have the same thing for Gj. Okay, make a distribution, and now compare these basically distributions. So any function you can compute in terms of how similar the distributions are, that would be the similarity between Gi and G distribution. So the only difference really is that whether you do frequent subgraph mining or you do a graph-led discovery, discover all the subgraphs and then define a similarity based on that. So that's your pattern discovery based kernel. Now there's a third type of kernel. Okay, so now we've done this. Now tell me what else can we do? So again, I give you two graphs, you have to define similarity between them. So this would be the third type of kernel. Let's think. What else can you do with two graphs? So we did the structural thing, we did the pattern stuff. So the third type of a kernel is, any ideas?
Content.
I mean, yeah, content based, yeah. I mean, assume that whatever we have done can be generalized to labeled, so if you have labels, I can do labeled graphlets, I can do labeled subgraphs, I can do labeled paths, So yes, definitely all those things can be generalized, but something different from that.
Cluster formations or something, groups,
Okay, sure.
communities.
Okay, you can do that, but I'm going to lump them in the same. I'm going to lump them in the same group as this. A subgraph can be community, it could be graph set, it could be frequent. All right, so let me. So this is what people do. Okay. So given two graphs, the other thing you can do is you can create what is known as the product graph. Okay, so the product graph is. So actually it's easy to verify. Let's do it. Right, so that's the advantage we have now. All I have to do is rerun this whole thing. Actually, first I have to set it up. So let's see what happens. I mean, I think it may have some trouble, but it's kind of like counterintuitive what will do. Which is, I think, what we think should have happened, right? So you're saying that basically keep on walking, as far as you can get, because it's like the inverse. So basically you end up being equally likely in any part of the network, as if the degree nothing matters, as if the structure is not there. You basically end up in pretty much the whole network. So now you have an answer. That's a good. Yeah, that's a good idea. But I can just maybe save it, right? Save to fire. So last thing, I'm just going to call it. Okay. It can be loaded up? Okay, I will not kill this yet, so we'll keep it. Okay, so I think that's all I have to show for today. So let me actually take a real example, and maybe I'll take a labeled example so that it's a little bit clearer. So let's say you have ABC, node 1, node 2, node 3, and this can be done for actually let's make ABA. Okay, so 1, 2, and 3 are the three vertices here, and here's another graph with just A and B. Okay. So this is graph 1, this is graph 2. So we define something called the product graph between G1 and G2. The product graph has actually pairs of vertices, okay, one from G1, one from G2. So all the vertices of the product graph, and I'm going to give this a number 4 and 5. So the product graph this is not the only class. You can do many more things, but this is one of the sort of commonly used approaches is that first you create the product graph. All the pairs I can think of, I need to put them. So it will be basically 1, 4, 1, 5. Okay. So there will be a vertex 1, 4, vertex 1, 5. 2, 4, 2, 5, 3, 4, 3, 5 like that. Okay, so this product graph has pairs, you basically pick any pair from the two input graphs, and so it's a much larger graph, of course. Right, the size of this times the size of that is the size, or is the order of the product graph. Now you have to put edges between the two things. So you put an edge if the edge is existing in both of the graphs. Okay, so if you look at the 1, 3 edge, so there's an edge between 1 and 3, and there's an edge between 4 and 5. So let me see, 1, 3. So this would be the edge that will be. Okay. So you put an edge if the edge, if the corresponding edge exists in both the graphs. So we will not put this edge because 4, 4 is not an edge in this graph. If there was a self loop, so if I actually let's add a self loop, then actually that edge would be present. Okay. So now in this case this edge would be present because 1, 3 is an edge and 4, 4 is an edge. Right? So this is the, I'm not giving you the full mathematical definition, just intuitively this is what happens in the product graph. Is that first you create the product of nodes and then you add these edges. So what does 1, 2? So 1, 2 is there and 4, 5, right? So actually, okay, now we'll have all those, anyway, so you'll have this also. You'll have 1, 5, 1 and 3, 1 and 3, 4 and 5. This edge will be there. 1, 2, 1, 2, 4, 5. Yes, this edge will be there. What else? Okay, now 2, 3, 2, 3. No, this one will be there. And 3, 4, 2. And maybe I missed something, but that's the idea, right? So in this product graph, interestingly, this also ties back to what we're going to do for the single graph case. Okay. So what you do now is that in this product graph, you look for basically the length of the walk, the diameter, and those kind of things. So two graphs are similar if those values are higher. Okay. So if you can get longer walks, okay, you can compute the clustering structure. So the idea is that you create a product graph which is sort of an amalgam of these two things. Okay, both the graphs are sort of embedded in this in multiple ways. And now you compute some structural properties of this. And the higher the values of those properties, the more similar these two graphs are. Okay, because as you can see, if they were identical graphs, then you'll get a much more denser looking structure. If they're very dissimilar, then the product graph is very sparse. So you can look at those things and see what happens. So the idea now is to extract path-based features from the product graph. And the features can be anything you want. Degrees, path lengths, eigenvalues, whatever. So that's a way of basically defining similarity between two graphs via this product graph. Alright, so and now actually once you have a single graph you can do other things. Okay, you can actually do pretty much the things that I'm going to do for the single graph case. I can do so let me talk about that first and then I'll come back to tie this whole sort of thing together. So these are basically the three main approaches. Okay, so to compute features, we do simple feature extraction, we do subgraph, communities, whatever, or we do some other stuff like this by combining things. And this is not the only way of combining graphs. There are probably other more sophisticated ways. You can do. Remember we talked about the chronicle graph, right? So actually you can do a chronicle product also. So the chronicle product would be actually this is I think similar to the chronicle product if I am not mistaken. Because the way we do this is replace every one of them. Yeah, actually, you know what? I think this is. I have to verify this because there might be slight differences in the way it's done. Because otherwise it would have been called the chronicle product graph. So I just say that yes, you can do product graph this way, and the Kronecker product graph would be to take this entire graph and embed that in each node, okay, and then add the loops and things between those. Whether or not you get the same structure, I'm not yet sure. I mean, I have to work it out to see that. But there is a relationship, okay. And so then you do analysis of those kind of structures. The only problem with this approach is that this is pretty much expensive. I mean, you're taking two graphs and you're multiplying them, you're growing it up, and then you're doing computation in this much larger space. So computationally, if the graphs are small, it's fine. If the pairs, so you want to compute the similarity between GI and GJ, and if both of them happen to be large graphs, then the product graph is going to be even larger, and so that might have some issues with the complexity. Alright, so that is that. Now let me go to the single graph situation, and what I want to do now is define certain notions of similarity in terms of graphs. Okay, so this is called diffusion kernel. And again, a very, very important idea in graph classification. So now the situation is the following. I'm talking about the other situation now, which is that you have only a single large graph. So I'll give you a single large graph. So for the multiple graph case, we have structural, you have subgraph A, you have product graph, etc. Right? So that's done. Okay, so that's pretty much a good sampling of the kinds of methods we can use to extract features and define similarity between them. Now we come to the single graph case. So there's only one large graph. Okay, so that's your database, that's the single large graph. Okay, now you have the nodes, and the nodes have labels. Okay? So this is positive, this is negative, positive, positive, and so on. So in this network, it's pretty much the same idea as before. The idea now is that I have to define a kernel or a similarity function not between two graphs, but between two nodes of the same graph. Okay? So here it was, you have to define the similarity between Gi and Gj. Gj belongs to the database. Here there's only one graph, and that's it, right? There's only one graph. And now, because you want to do node classification, you have to define the similarity between two nodes. So basically you have to define between Vi and Vj. So the idea here is to extract the similarity between two vertices where Vi and Vj belong to just one single graph. Right? What is the measure? How are we going to extract that? So here we can start simple. We can do some simple things first before we do a little bit more complex. What you can do is you can say that two nodes, let's say Vi and Vj, are similar in terms of how many neighbors they have in common. It's very, very. In fact, that works out pretty nicely in social networks. That two people are similar to the extent in which they have common friends, for example, or they have common interests or whatever. So this is known as the degree of assortativity between two vertices. Assortativeness. Essentially, what you're doing is you're computing some sort of a correlation, okay, in terms of the neighbors. So you just look at the number of common neighbors. So you can define those. You can define, of course, shortest paths between them, right? You can use notions of shortest paths. So here the space is pretty much open. You can do lots and lots of ways of defining the similarity between two. So it will be the number of common neighbors, the number of common neighbors with the same label, the number of paths between them, right? All those things we can apply here to define some notion of similarity between them. But that would be just one level. Okay, so what we want to do is we want to go beyond that. We want to do, so these diffusion kernels are essentially the idea of information propagation. You say, I'm going to start some sort of a diffusion process from here. I'm going to start another process from here. And I'm just going to let things happen. And then I'm going to compute some sort of overall score, okay, how similar they are. So that notion is the one that I want to basically try to describe now, is that you can define a basic similarity function, but I want to go beyond just the basic one. I want to use the structural information of the entire graph to help me define the similarity. So this is information flow in the whole network, and then we extract similarities between them. So this is basically, the starting point is that we start with some similarity matrix. Okay, so whichever way you define it, we don't care. The idea is to start with some similarity matrix. So compute a matrix S, okay, which is just going to be the similarity between Vi and Vj. So actually I could just say the similarity between Vi and Vj for all. So this matrix, right, so essentially it's a matrix, the ijth entry contains a similarity value. So the only thing we impose on the similarity is, again, it should be symmetric, okay, and it should be non-negative. Should be 0 or higher. So basically we can say that the similarity ij should be the same as ji, and sij is greater than equal to g. But these are the only two conditions we impose on the starting similarity. There's no other condition required. If it has other conditions, if it has other properties, then some things become easier, which I'll explain. So that's why we start with a similarity matrix. We don't start with a kernel. Okay, so I haven't yet talked about kernels, but for a similarity matrix to be a kernel matrix, it has to be positive semi-definite. Okay, so that's the only other. So a kernel is a similarity matrix that is PSD, okay, positive semi-definite. And remember, positive semi-definiteness, what that means is that the eigenvalues are non-negative. Right? So that's what we really want. So you just either have a plain similarity. Plain similarity only needs these two conditions. If you want to make that into a kernel, you have to add this condition. In that case, I can call it a K. Okay? So I'll use the big K for a kernel. And by definition, a kernel will be positive semi-definite, symmetric, non-negative, and all that sort of stuff. But we don't need to start with a kernel. We can start with any similarity that you want. Now comes the notion of basically walks. So this is where again we tie the notion of a random walk. So if you start with a similarity matrix, the idea is that I can take powers of that matrix, and the powers of the matrix essentially correspond to some sort of a walk in the network. So this is our basic, the most simplest kernel is what is called as a power kernel. Let us start with S, okay, and simply compute the L power. If you want to do a walk of length L, okay, walk of L hop. It's like, when you take the powers of the matrix, it's going to give me all the walks, right, up to length L. So basically, how many walks do I have, starting from one vertex and ending up in the other? So essentially, we are saying that this power kernel, the basic intuition is that the power kernel tells me, if I want to compute these two, the similarity between Vi and Vj, it says that within L hops, right, what is the likelihood that I'll end up in, like how many times do I basically end up in Vj? How many, rather, is the number of walks from Vi to Vj up to length L. Okay, that's the power kernel. Okay, there's no probability there, just how many walks there are. So if you just take an adjacency matrix and you compute the powers, it will tell you the number of walks of a certain length, up to a certain length, from one vertex to the other. So that's what it would be. The number of walks up to L. So you can try L10, L. So, but you're allowed to go back and forth. So if you want to say, like a walk 4, so you can go from here to here, you can go from here to here, you can go there 3, and you can come back 4. So that will still be a walk. So this will compute all the number of walks up to L.
So, it is the weighted sum of weighted.
No weight yet. So that we'll talk about later. This is just a power, is just the number of walks. There is no weighting being done. And just
walk in adjacency matrix at the power k. Then I just give the number of walk between V and Vj.
yeah.
But this matrix is different from adjacency matrix.
Yeah, but you can think of it as a weighted adjacency matrix, right? Because the similarity tells you how similar they are. So if it's 1, you'll get the normal notion of, the number of, like the length of the walk. But this is sort of like the total weight,
Yes.
total information that goes up to length L. Yeah. Okay, so that's our basic, power control. It's not very interesting because, it's sort of unconstrained. You can pretty much do this. So we can do a little bit better than that. So the next notion is that of, and this is actually a very, very important kernel. It's called the exponential diffusion kernel. So you see what we're doing here. We are doing something very interesting. We are adding up walks up to length L. Okay, so the idea is that do a walk of length 1, do a walk of length 2, do a walk of length 3, length 4, length 5, up to length L. So that's this part here. In fact, not only that, it's the summation over all possible lengths. Okay, this is the beauty of this. It's an infinite sum of all the walks of all possible lengths. You can imagine. Okay, so the two nodes are going to be similar based on basically the total flow of information between the two vertices. Okay? So that is the total weight that goes from one to the other over all possible walks. Now, of course, if you just keep on doing this and if you didn't have this part here, well, it will become an infinite sum. I mean, all the values will be infinity. Basically, keep on going and going and going because there's no limit on the number of, how long I can go. So that would be a useless kernel if you want to do just sums of powers up to length L. So the only way this is practical is if you exponentially decrease the weight. So the longer you walk, the less influence you have in the total summation. So what this does is it actually counterbalances. So every time you increase, right? Every time you take the Lth power, that means you're doing one walk of a longer length. You're going to exponentially decrease the contribution of that walk. And that exponential decrease will come from the L factorial. Okay? So that means the longer you go, very soon you basically have no contribution from that, from very long path. So if L goes to infinity, obviously infinity factorial is something even bigger than infinity. It's practically there's no contribution to the current, to the similarity. So we're saying that you contribute most if you are closer to the vertex and you contribute less and less, the more further away you are in the network. And then we also have this beta parameter that sort of acts as also a sort of a dampening factor. So beta is just some constant that we pick up, and so we just say it's the power of the matrix 1 over L factorial and beta to the power L is some scalar to the power L. If you actually expand this turns out to be this infinite expansion. But for those of you who are familiar, this infinite expansion is exactly the exponential function, actually. So the exponential function is defined precisely in this way. So this is called the matrix exponential. So this is called the matrix. Actually, I have it written here. So this term, like this infinite expansion, where you take all the powers of all the lengths, but you sum them up in a exponentially decaying manner, that is called the exponential matrix. And the beauty of this matrix is actually that it looks like it would take infinite amount of time to compute this, right? But this is actually a converging sum. Okay, so it actually converges. And so it turns out that mathematically it's like extremely, extremely elegant result. The eigenvalues, the eigenvalues of this matrix, which is what you're normally interested in, the eigenvalues are simply the exponential beta times the eigenvalue of the original matrix. So basically, just so all you have to do is you have to just compute the eigenvalues of S. You just have to do a simple computation of the eigenvalues of S, and and each one of those. So basically, the mathematically, I'll go over this maybe again next time. But mathematically, what this means is that you take S and you compute lambda 1, lambda 2, lambda n, right? So compute just the n eigenvalues for S, and of course the corresponding eigenvectors. So the U vectors are the eigenvectors of S. Okay? So U1, U2, Un. So for every eigenvalue, there is a corresponding eigenvector. So you just do this once. Okay. Now the beauty is that for this kernel, because this actually defines the positive semi-definite kernel. For this kernel, this whole exponential summation, the eigenvectors are precisely the same as the eigenvectors of S. It doesn't matter if you do this, exponential stuff. The eigenvectors are exactly the same, and every eigenvalue of this kernel matrix is simply beta times lambda 1 e to the power beta times lambda 1, e to the power beta times lambda 2, and so on. So basically we can say that lambda I prime is equal to simply e to the power beta lambda I. So this is for k. So this is actually, in other words, very cheap to compute. I mean, even though it looks like a very expensive operation, you're doing summation over all these things, but mathematically one can show that it's just, eigenvectors are the same. So eigenvectors of k are the same as the eigenvector of the initial similarity matrix. The eigenvalues are simply related by this exponential function. And so it's very easy to compute, so we can actually compute this kernel, and this will define the similarity between. So the similarity is given by the ij entry of this kernel matrix. Whatever the value is, that's the similarity between node I and node j. Because this matrix is going to be an n by n matrix. So k is an n by n matrix. And the ijth entry of that matrix defines the similarity between the two nodes. So now we have a way of computing the diffusion and the flow. Okay, so alright, so I think alright, so there are more things to cover, but we can take a, are we going to stop for the tea break? Okay, so we're going to stop for the tea break, and then I can take questions and other things after that.